Okay, so let's get started. So, good morning, everybody. Um, First of all, let me share my screen. Everybody, could you see my screen?
Yes.
Yeah,
Yes.
the chapter title Three-Phase AC Circuits. Um, so, this is our first chapter, for the energy conversion course. This is very basic chapter, so you all have to understand it properly. Uh, Maybe you remember that in the circuit analysis 2 course, you all have studied about this, but in this class, we will be looking extensively. In addition to this class, we will be spending 2 more class on this chapter, followed by several numerical problems. So the first of all, I am showing in this slide the advantages of three-phase system over single-phase system. So you all know that at your home or for any customer, most of the loads are single phase base. There is phase and neutral. Although industry use three-phase system, but most of our load is single phase. But here we are going three-phase AC power generation system. So what is the motivation behind that? What is the philosophy behind that? So you see, I have pointed out several bullet point like efficiency increase, economical, then output power increase, voltage or current level increase, maintenance decrease. So these all are the beneficial feature of the three-phase system over a single-phase system. Now, if you see this diagram, that will help you understand those 5 points. So everybody say this is the three-phase power generation system. So therefore, this circular body, this is called the stator, or sometimes it is called armature, on which the coils are mounted. So in this case, you know that A prime, this means there is a coil, A is one end, A prime is the other end. So A prime, B prime, then C prime. So therefore look A prime, then C prime, then B prime, they all are properly displaced by 120 degree phase. And then from A prime, C prime, B prime, the output terminal are being taken and given the name A, V, C. Then the other end, like A, V, and C, you all see, they all are connected together at a common point, which is the neutral line. So this means this is the three-phase and on neutral line system. And then in between, you see, there is a magnet having the North Pole and South Pole. And you remember that in the last class, I was explaining you, there could be a prime mover or the turbine together with a shaft to which this magnet will be attached. So this means this magnet will be moving, it will be rotating. So now once this magnet rotates, this means that this is North Pole, South Pole. You see the one pole at a time is going close to each and every coils. So then the voltage will or the power will build up on these coils. So this is the output. Now, the first bullet point of the advantage is efficiency increase. So you all know the definition of efficiency, output over input. So in this case, input is this magnetic field rotation, this rotation, and that is coming from the prime mover. So now if you just put only one set of coil, then only one set of voltage will build up, which is the single phase. Now, here you see that because this magnetic field is moving, So we are taking the benefit of having three sets of coil so that simultaneously, just with 120 degree phase shift, voltage or power can be built up. So this means that we are getting more output with one input. So that's why the efficiency increase. Now you can make argument that no, I will not be using this arrangement. I will be using just one set of coil and only one magnet, and then I will build up another set of coil with another magnet. So you can make three separate systems, but then that will not be economical. So your output might be the same, but you will not. It will not be economical. It will not be cost effective. So that's why this is economical. And then clearly the output power increase, voltage level, current level increase, but the maintenance decrease. So as I mentioned, if you have three separate single phase system, then for maintenance, for overhauling, or if there are any issues, then you need three engineers, three operators to work. So here you see, because it is on single compact system, therefore only one operator is enough. In that sense, it will have less maintenance. So the maintenance decrease. So these are the motivations or these are the main points of the beneficial feature of the three-phase system over the single-phase system. So everybody, do you understand?
Yeah, it makes sense. I remember
Yeah.
from last semester.
Yes, yeah. I mean, this is, as I told you, this is kind of exactly the same as the three-phase system that you have learned in AC circuit. But here we will be looking a few more new things like power factor correction and three-phase power measurement, followed by several new problems. Okay, so moving forward, so is it three-phase power generation system? So this means earlier you see this is the output terminal, F phase, B phase, C phase, or three phase. So how those output voltage look like? So here are the pictures. So here, although it is written like phase 1, phase 2, phase 3, but basically phase A, phase B, and phase C. So you see the pattern, it is starting from 0 point, and it is like pure sinusoidal waveform. Then the second down, phase B is getting started after 120 degree. If you compare from the zero position, zero line. So therefore it is 120 degree and then going on. And then again another 120 degree upward. The phase 3 is getting started. This means that if you compare peak to peak, this is the peak of phase 2, this is the peak of phase 3. Peak to peak is like 120 degree. This peak to this peak 120 degree. Again, this peak to phase on is getting repeated, that is 120 degree. So accordingly, so those three phase voltage are expressed VA, and you all know these are the time dependent function, time dependent variable. So VAT, Vm cosine of omega t, then Vb minus 120, then Vc, it should be minus 240, but then to make similarity, here like 120, 120, so anti-clockwise, it is plus 120. I mean, if you go clockwise, minus 240, but then anti-clockwise, plus 120. So that it is easy to remember that B phase is minus 120, but then C phase plus 120. Okay, so further moving forward. So two important terminology. One is balanced system or symmetrical system, and unbalanced system, unsymmetrical system. I mean, when it is a single phase system, then there is no question of balanced or symmetrical, unbalanced, unsymmetrical. But once it is three phase system, then whether it is balanced or unbalanced, that is very important. So what's the definition of that balanced system? So balanced system means voltage or current magnitude of all three phases should be equal, and all three phases should be displaced by 120. For example, just see this example. AA prime. These are the like line to line voltage, 120, or reference angle is 0. Then after 120 degree apart, minus 120, then another minus 120. So total minus 240, but then anti-clockwise it is plus 120. So therefore, this is the example of the balanced three-phase source. Now, what is the unbalanced or unsymmetrical? The voltage current magnitude of all three phases are not equal. I mean, three phase could be displaced by 120 degree properly, but their magnitude should be unequal. For example, in this case, all three phases have same magnitude, 120, 120, 120. I mean, they are displaced by 120 degree, but we are assuming their magnitude is also 120 volt, 120 volt, 120 volt. Now, if you see that here it is 120, but it is 110 or 100 or 90, or these two could be same, but this one is different due to various reasons. I mean, this unbalanced thing happens due to some fault, due to some disturbances, some other issue on the cables. The system might be unsymmetrical or unbalanced. So, and then there is severe impact. So we will be discussing later what is the adverse impact of having the unbalanced system. So at this point, just keep in mind that unbalanced or unsymmetrical system is not desired because it has negative impact on the system. There could be circulating current flow. For just an example, you can easily understand. Here it is 120 and then 120 and proper phase difference. But if it is 90 volt, then there would be circulating current flow from A phase to B phase because of the voltage difference. Now there is no voltage difference, voltage are equal. So there should not be any circulating current flow. Or for example, there is voltage difference between this one and this one, then there should be circulating current flow. And if there is any circulating current flow, then that will cause some loss, voltage drop in the system. Gradually system will be ineffective and inefficient. So we'll be discussing these things later. So just keep in mind that unbalanced system is not desired. Okay, so then moving forward, uh, this one, because we are discussing about three-phase system, just note that three-phase systems are two types. One is called star or Y, other one is called the delta. Therefore, I mean, see these two pictures, this is the right side, this one is the delta connection, and left side is, it looks like the letter Y. If you see this one, this is one arm, this is other arm, and this is other arm. So if you look in this way, then it looks like the letter Y. Accordingly, it is called the Y connection. But also, it looks like the symbol star, that's why it is called the star. And it looks like the symbol del, accordingly it is called the delta. So there are two systems, but you see the first of all the delta pattern. So this is one set of coil, this is another set of coil, another set of coil. I mean, there is voltage source to indicate that each set of coil are producing voltage. But then you see that how they are connected. This is on end, C prime end of this coil, and for AA prime, this is on end. These two are connected together, and then it is going to the lines, I mean to the grid. So similarly, these 2 points are connected and it is going to the grid, these 2 points. So this means here there is no common point, but see the Y connection. This is on coil, this is other coil, this is other coil. So all three are connected at a common point at this point. And then this is going towards the grid to the line. This is going towards the line. This is going towards the line. But there is a common point of all three sets of coil. This means that you can connect another line, which is the neutral line here at this point. So therefore, this three phase and then the neutral system. But here you compare, there is no common point. So this is on coil, this is other coil. They are connected at this point, but this coil is not connected at a common point. So this means for delta connection, you can't connect any neutral line. So everybody, could you follow me so far?
Yes.
Yes.
So just keep in mind, therefore, then now in real life, in outside, for example, you are going a long way, you are driving on highway, that you might see several cables. Typically, you might see 8 cables. Therefore, those are typically the Y connection. Therefore, this 3-phase and on neutral line. So this means on, 2, 3, and then neutral 4 cables, and there should be another 4 cables, another Y connection. So that is just for the reliability purpose. In case something happens in on 3-phase system, so that still power flow continues with the help of other 3-phase system. That's why typically you might see 8 cables. Those are not the delta connection. Those are typically the Y connection. I mean, there are relative advantage, disadvantages. I mean, you see, as I said, that you can connect the neutral wire here. So in that sense, you have the flexibility to use. Uh, for example, industry can use 3-phase with the neutral system. At our home, we can use single phase and neutral system. You cannot use this thing at your home, or industry can't use. But in this case, you are saving the cost of the neutral line. You don't need the neutral line. So the question comes where to use the delta connection. So there are certain places on the transmission line and distribution line when customers don't need to use any power. In that place, use the delta connection just to save the cost of the neutral line. But once it is nearby the customers need to use the power, then it should be the Y connection, because you need the neutral line, and ultimately that neutral line will be connected to the safety grounding, because it should be grounded for proper or full safety. But because there is no neutral connection here, so you can't make it grounded. That's why typically this arrangement use in a portion of the power network where people don't need to use power. For example, 100-mile lines are going on, but people don't need to use power from there. So in that place, instead of this one, use this system just to save the cost of the neutral cable. Okay, so over the time, you all will be understanding, that will be fine. Now, moving forward, see this one. So now several important note, as I said, the currents through the actual elements, source or load elements, are referred to as the phase currents. And then voltage across actual elements, whether it is power source or load elements, referred to as phase voltage. And then currents through the XYZ are called line current. So let me go back, then it will be clear. You see the first Y connection. So this on the actual cable, this portion, A prime, C prime, B prime. So from A and A prime, you can call this thing its phase. This is on phase, this is second phase, this is the third phase. So therefore, when current is flowing through A prime, this is phase current. B prime, this is phase current. But then that's X, Y, and Z we are calling, because these things are getting connected to some grid or to some other line. Therefore, these are called the line current. So therefore, this portion is the phase current. This is phase current until this point phase. But once current is flowing here, that is the line. So therefore, clearly you see, because this line is connected in series with this phase coil. So in this case, phase current and line current are the same. But in this case, you see, these are the line current, and then these are the phase currents, because these are inside the coils. But in this case, clearly you can see this line current is not the same as this phase current, because here it is the combination. There is a common point of this coil and this coil, so you can't say that this current is the same as this one or that one. So therefore, in this case, the current flowing through this coil, this coil, this coil, those are the phase current. But current flowing through X, Y, and Z going towards the some loads or some other portion of the network or the grid point, those are the line current. Okay, then in case of the voltage, you see, there is a voltage here. So if you attach a voltmeter and if you measure the voltage across C prime coil, you will get on voltage. But then if you attach a voltmeter between point X and Y, that is also another voltage, but both voltage will be the same, because essentially this is the same point. So this means in this case, this is called the phase voltage when you are measuring voltage across only one coil. But once you are measuring the voltage between X and Y, although the voltage magnitude will be the same, but this is called the line voltage, line to line voltage. Similarly, if you add a voltmeter across this coil, you will get some reading, that is the phase voltage. But if you attach a voltmeter between X and G, then still you will get the same voltage, but that is called the line voltage or line to line voltage. So similarly, you see again in this case, if you measure a voltage between A and A prime, you get one voltage. But then if you connect a voltmeter between X and Y, you would get a different voltage. Because you see, because from X to Y, these two coils are involved. Similarly, if you add a voltmeter between Y and Z, these whole portion, these two coils are involved. So in this case, voltmeter reading will be different. So if you connect a voltmeter between X and, if you get 120 volt, just example, versus if you connect a voltmeter between A and A prime only, you will get lower voltage or different voltage. But then this voltage, when you will be measuring voltage across the element itself, that is called phase voltage. Once you will be measuring between two line points, that is called line to line voltage. This is what is stated here. Once again, everybody see, the currents through the actual elements, source or load, are referred to as phase currents. And then voltage across the actual element are called phase voltage. Currents through the X, Y, G are called the line current. I mean, why I am emphasizing this thing? I mean, in the numerical problems, sometimes we will be using the term line current, sometimes we will be using the term phase current, sometimes we will be using the terminology phase voltage, sometimes we will be using line voltage or line to line voltage. That's why these definitions are very important. So therefore, for example, everybody, let's have a look this example of line and phase voltage. So see first the left side, this means this is the star or Y connection. So everybody see, this is phase A, there is one coil, this is phase B, this is phase C, but then here there is neutral line. As I told you that Y connection will have the neutral. Delta cannot have any neutral. There is no provision to connect any neutral line there. So anyway, so see, like 120 volt. So 120 voltage, you see the arrow, it is between phase A and then the neutral. So this means that what you are measuring, essentially you are measuring your voltmeter, one connection point is here, then other point is here. So that's why this is called, when it is between phase A and neutral, this is the phase voltage. Similarly, you see between phase C and the neutral line 120, this is also called the phase voltage for phase C. Similarly, between phase B and C 120, this is the phase voltage. But now look this one, 208 volt, that is between phase A and between phase B. This is called the line voltage or line to line voltage. Similarly, between this one and this one, 208 volt, that is called line voltage. And again, similarly, between phase B and say 208 volt, those are the line voltage. And if you have a calculator, you do like 120 multiplied by root 3, that should give you 208 volt. Like 120 multiplied by root 3. So this means that in case of a three-phase Y connection system where there is a neutral line connected, the relationship between line to line voltage and phase voltage is that line to line voltage equals to root 3 times the phase voltage. But look, in this case, three-phase delta, as I told you, in this case, that 400, just another example, 480 volt between this point and this point, meaning that this is the phase voltage, but then the same voltage applies between phase A and B, the same. So that's why in case of delta, phase voltage and line to line voltage are the same. Just keep in mind, in case of delta, it is not related to root 3 times because phase voltage, line voltage are the same. The same thing goes for the other phases. But it is very important to remember this one. In case of Y connected and with neutral lines, the relationship between line to line voltage versus the phase voltage is root 3 times. So phase voltage will be root 3 times lower than the line to line voltage. Everybody, could you follow me so far?
Yes.
Okay, great. This is very important. I mean, as a baby engineer, like you must understand, and you will be asked this type of questions in the job market and in the FE exam, especially for this one. Yeah, because in this
I
case,
have a question about the delta. So
okay,
the voltage is gonna be the same on the line to line. I mean, it's not gonna be. It's not gonna change.
yeah,
That's a,
yeah, yeah. Because you see this one. For example, you have a voltmeter here, and you know that voltmeter needs 2 point, right? Two terminal. So, for example, you have a voltmeter here. You are connecting one end here, other end here. So you are getting 480 volt, but then connect the voltmeter here between phase and B. Therefore, you compare. Ultimately, this point is this point, and this point is this point. That's why you are getting the same voltage.
okay. I see. Thank you.
Yes, but you see, I mean, here we are just looking the voltage, left side and right side figure. But everybody see, in case of delta, for example, if you connect a ammeter here to measure the current, so the current flowing through this line, I mean the phase A, but then if you connect a ammeter across this coil, will these two current be the same? No,
No.
No.
no, no. So because it is not series connection. The issue is that at this point another coil is attached, so it's different. But everybody see, in this case, if you connect a ammeter here, the current is flowing, and then if you connect a ammeter inside the coil, this current will be the same because this portion is connected in series. So therefore, in case of the Y, line current and phase current are the same. In this case, line voltage and phase voltage are the same, but line current and phase current are different. So here there is a root 3 relationship. In this case, the line current should be root 3 times the phase current. And in this case, line voltage or line to line voltage should be root 3 times the phase voltage. Everybody, do you understand?
Yeah.
Yes, this is very, I mean, definitely you, I mean, you have to, I mean, from today, you have to keep this in mind forever, and you will be frequently asked this type of question in real life as an engineer when you are working in any industry, not just power industry. Frequently, you yourself need to make some design calculation. That time you have to keep this thing in mind, that what you are calculating Is it voltage or current? And are you dealing with delta connection or are you dealing with Y connection? Accordingly, you have to calculate the voltage and current relationship between the line quantity and the phase quantity. So this is very, very important. Okay, so
Dr. Ali,
yes,
so if I understand correctly, the voltage across a phase and neutral in the Y setup
okay,
is 120, and then the voltage across two phases is 208.
yes.
And then is there a neutral for the delta setup?
No, for delta, there is no neutral.
Okay,
For delta, there is no neutral. See, the neutral is connected only with the Y connection because there is a common point. But in this case, you see, there is no common point among all three phases. That's why there is no neutral line on the delta. Is this your question?
Yes, thank you.
Okay, thanks. Okay, so therefore, again, once again, after the class, you all again, please look all the slides. I mean, this is very, very important, and you all must understand these things. And as I told you, the very first lab will be about the three-phase system. So therefore, I mean, these slides, will really, really help you. And these are like all, I mean, realistic. Even you might face any problem at your home. That time you have to keep these things in mind, and accordingly you have to solve the problem. Okay, then moving forward. Yes, here you see that I am concluding those things that I was explaining in the previous slide. Everybody see? For delta connection, the phase voltage and line voltage are identical or the same. So this means VLL. Just keep in mind here, phase voltage is clearly the across the phase on setup coil, but line voltage means line to line voltage. Now in literature, frequently just line voltage is used. So, but line voltage means line to line voltage. So you see, line means this is line, this is lines, although these are written like phase A, phase B, phase C, but basically this is on line, this is other line. When the voltage is between two phases or between two lines, that is simply called the line voltage. Line voltage does not mean that it is only across one line, because everybody understand, because this is voltage. To measure the voltage, you must need 2 points. With only 1 point, you can't measure the voltage. I mean, for current measurement is okay because it is connected in series with one coil. But to measure voltage, you must need two coils. So this means this is actually line to line voltage, but frequently in literature, in books, anywhere, simply they write just line voltage. But keep in mind, this is line to line voltage. That's, you see, VLL, VL dash L. This means between two lines equal to V phase. This is the phase symbol. For Y connection, the phase current and line current are identical or the same. I phase equal to IL. For delta connection, the magnitude of the line current is root 3 times the magnitude of phase current. As I was telling you, that in this case, if you measure current here, if you get the, for example, current value 208 ampere, just random example, and if you measure the current across this coil, you will get the reading here 120 ampere. This means this line current will be root 3 times the phase current. So that is the meaning of this one. The magnitude of the line current is root 3 times the magnitude of phase current. For Y connection, the magnitude of the line to line voltage or simply line voltage is root 3 times the magnitude of the phase voltage. Therefore, these things is very, very important to solve the numerical problem and to understand many concepts. So is everybody fine so far?
Yep.
Okay, great. Now look, one more important, very, very important slide. And then we will jump into discussing some numerical problems. So, and everybody please, concentrate here, 100% concentration. This is, if you just keep in mind in your head these slides, then you can solve any problem. I mean, this slide is kind of the numerical summary of this chapter. So what I have written, again, like I am recapping those things. So for delta connected system, line voltage VL equal to phase voltage VP. So again, keep in mind line voltage means line to line voltage. Line current IL is √3 times of the phase current. So therefore, right soon, once we will be solving numerical problems, you have to utilize these concepts, these conclusions. For Y-connected system, line current IL equal to phase current IP. Line voltage VL √3 times of phase voltage VP. Now here say total three-phase real power. So you all know the concept of real power and reactive power, apparent power that we have discussed and you have learned in case of AC circuit analysis, circuit course 2. So now because I have the three-phase system, so for the three-phase system, and I am assuming this is the balanced system. If it is balanced system, then total three-phase real power 3 times of VP IP cos theta. So everybody remember that VP IP cosine of theta, where theta is the phase angle between voltage and current. And you see, I have used the symbol phi to indicate the phase quantity. Everybody see, this is phase voltage VP, phase current IP. So therefore, PP symbol represents the phase quantity. So therefore, VP IP cosine theta, this is for on phase. For example, phase A or phase B, phase C. And because this is balanced system, all three phases will have the same amount of real power. That's why I am multiplying by 3. Now if it is unbalanced system, then you can't use this equation. You have to, sum up phase by phase. For example, VP IP cos theta, this is for phase A, plus VP IP cos theta for phase B, plus VP IP cos theta for phase C. Because in case of unbalanced system or unsymmetrical system, voltage magnitude or current magnitude will be different. So you can directly multiply by 3. You have to, sum up or add up phase by phase. So therefore, you remember this equation is valid for the balanced system only. Okay, now these quantities are in terms of the phase, but in real practice, for example, you went to market and you purchase a three-phase device. For example, you purchase a three-phase induction motor for an industry, just an example. So on the nameplate of the machine, you will be seeing it is written line voltage is, for example, 208 volt, frequency 60 hertz, temperature, withstanding capability. There will be various information, nameplate data. So therefore, voltage quantity always expressed in terms of the line voltage, not in terms of the phase quantity. That's why, although these equations is valid or right for the total three-phase real power, but because in realistic system, voltage is expressed in terms of the line quantity, like you have to use this on VL, or you have to use this symbol VL. That's why we have to convert this equation, we have to represent this equation in terms of the line quantity. That's why everybody see the next line, real power. So here it was in terms of VPIP, but here you see √3 VL IL cosine of theta. You see how the symbol changed. Not VP, it is VL. Not IP, it is IL. And in order to do that, in order to change the symbol, then it is not 3 here, it is √3. And what I have written, delta or Y system. The same equation is valid, same equation is applicable to both systems. delta on y. You need not to be worried. So therefore, from today, everybody, you will be memorizing this equation throughout your life, that real power for three-phase system, root 3 VLIL cosine of theta. So where VL is line-to-line voltage and IL is the line current. Now, the thing is that how that magic number root 3 comes. Here it was 3, here it is root 3. So how that comes? So see the calculation on right side. So this is our basic equation, right? Like 3 Vp Ip cos theta. So for delta connected system, you see this 3 is this 3, but look the top conclusion for delta connected system, line voltage VL equal to phase voltage Vp. So I am substituting Vp by VL. This is that VL. Now see, I have to replace with line quantity this IP. So come back here, the second line current IL is root 3 times of IP. So this means I have to substitute this IP by IL. So IP is IL over root 3. So that's why everybody see here. For this IP, this is IL over root 3. So cos theta is cos theta. Then now see, this root 3 is here, but 3 is here. So it will be cancelled and root 3 will go there. So the expression will be root 3 VLIL cosine of theta. And then for Y connected system, I mean, why I said that this equation equally valid for both delta and Y system. Look the Y connection. Again, this is my equation. So this equation is valid for both delta and Y system, this basic equation in terms of the phase quantity. So now this 3 is this 3, but what is the Vp? Look the Y connected system. VL is root 3 times of Vp. So this means Vp is VL over root 3. That's why it is VL over root 3. And what is the relationship IP and IL for Y system? IL equal to IP. So that for this IP, here it is IL. Then again this root 3, root 3. So root 3 is coming here. So this means in this case also a root 3 VLIL cosine of theta. So that's why everybody you will be keeping in your head root 3 VLIL cos theta. Never ever put just the 3 here. Like frequently, like students make mistakes in the exam or in the homework, they use 3. It is not 3, it is root 3. So if you put 3, then it is, you must put VPIP. But as I told you that in real practice, in every quantity is expressed in terms of line voltage, line current. That's why please use the root 3 here. Then similarly, the reactive power, reactive power is VI sine theta. This means 3 VPIP sine theta. Say accordingly, because of these conversions, root 3 VLIL sine theta. And the same equation applies to both delta and Y system. It does not matter it is delta or Y system. Then afferent power is, if you remember that power triangle, I mean, soon I am showing you. So S is root 3 phi square plus q square equal to phi plus jq root 3 VL into IL. So therefore, because cos square theta plus sin square theta, that will be 1. So that's why ultimately you are getting root 3 VLIL. So therefore, this is called the apparent power. And then this is the power factor. You all know the definition of power factor cos theta is real power over the apparent power, this one. And then keep in mind, so the real power is expressed in terms of what? Reactive power is expressed in terms of reactive volt ampere, simply the var. Apparent power is expressed in terms of volt ampere. And then this is the power factor. So therefore, just a moment, temporarily, let me. Can you see the whiteboard?
Yeah.
Okay, great. this is P, this is Q, and then this is S. So here is the angle theta. So therefore that power factor is the cosine theta. So therefore this is the phi over S. So and then as I told you, for example, this one is real power and it is expressed in watt. And then this one is reactive power. This one is expressed in var, and var is reactive volt ampere. And this one is called apparent power. This one is apparent power. And this apparent power AC is expressed in terms of volt ampere. And this one is the power factor. So therefore this power factor, this one actually, this is the cosine of theta. So and then this is called the power triangle. So this is called power triangle. So you will be keeping in mind, I mean, in the FE exam, you might be asked this question, what is the power triangle? Then you have to show this triangle and then you have to explain each quantity. So, and this is very, very important. If you can just remember this slide in mind, then you can solve many, many problems. So therefore, according to this P equal to, so let have P equal to, that I was explaining, that root 3 VLIL cosine theta, and then Q, this reactive part, again similarly, that root 3 VL IL sine theta. Yes, and then that is root over this one. That's why ultimately S is getting, because S is root over phi square plus q square, you make phi square q square. So cos square theta plus sin square theta, it will be 1. So ultimately it will be just root 3 BL into IL. Everybody, could you follow me?
Yes.
Is this fine? Yes. So therefore keep in mind the unit. So this one is the real power, which is root 3 VLIL cos theta. This one is Q and this one is apparent power S. And this is that power factor angle. And this theta is the angle between voltage and current. So, and then unit of this one, it will be volt ampere. Everybody keep in mind. This unit is volt ampere, apparent power. That's why root 3 PLIL. But this one watt and this one unit is var. So therefore, depending on magnitude, how big it might be kilovar, megavar, kilowatt, megawatt, kilovolt ampere, or megavolt ampere. So you understand this one. So let me save this one. Okay, so let me go back again. Okay. Sorry. Okay, so I was in this slide. So then everybody, I think, so everybody, you have to keep this slide in mind to solve the numerical problem. Therefore, let's have a look some example. Everybody see this practice problem. As I already mentioned, we did similar things in the circuit course, if you remember, but in this course, we will be doing much more numerical problems and few other concepts. Maybe not today, in the next class and then the other class. Everybody read the statement assume that the phase voltage of a Y-connected source at its terminals are given as VAN this amount, VBN this, and VCN this number. Determine the following: the line voltages of VAB, VBC, VCA. You see, these are the phase voltage. Can you see the symbol? N means the phase to neutral, phase to neutral. And then you are asked to find out the line voltage, VAB, VBC, VCA. And then second question, if a balanced Y-connected three-phase load of GN equal to GBN equal to GCN is 10 at an angle of 30 ohm is connected to the source, then find all the phase and line currents. So these two are the questions. Now here, like I did the solution. So everybody see, this is the Y system. So I have written, you see, VAN, VBN, VCN. I have drawn three coils, and these are the line is going. Okay. Now these quantities were given. If you see this, like VN this, VBN this, VCN this. So just I wrote down those three quantities. Now, first question is that you have to find out VAB. So therefore everybody see here, what is VAB? This is from this point to this point. So because you all know that AC quantity are like phasor quantity or the vector quantity. These are not the scalar because there is angle, phase angle is involved. So you must go vectorically. So that's why what I am doing, VAB is VAN. Everybody see my PowerPoint. Sorry, my pointer. VAN plus VNB. I am going in this direction because this is vector. So first I wrote that on. But look, these given quantities, VAN was given, VBN was given, VCN, NA, NB, NC. In that way, those are not given. As I said, because these are the vector quantity. So it is BN or NB, that is important. It is N or it is NA, that is very important. So that's why, because these quantities were given in terms of VNA and CN, I am changing VNB to VBN. So because this is vector, that's why I put a minus sign here. So therefore VN is VN, but it was plus VNB. When I am using VN, I am putting a minus sign. And then substitute those values, VN and for VBN, this one. And then by polar rectangular conversion, you keep going. Finally, I got 480 at an angle of 30 volt. Then similarly, if you do for VBN, so VBN will be, sorry, this will be, sorry, I made a mistake. This will be VBC and this will be VCA. I will change this slide. It will be VBC, it will be VCA.
Your audio cut out again.
Sorry, what you said? Okay, anyway. So therefore, if you see the VC, this means VBN plus NC. This means VBN minus.
Turn off your actual video. The bandwidth might be better, and just.
Oh, okay. Okay. So therefore, everybody, like, do you understand this calculation? Everybody, do you understand this thing? Is there any questions on how to calculate VAB?
We couldn't hear you that entire time.
Okay, can you hear me now?
Yes, we can hear you right now.
Oh, okay. There
It
are
was just
some.
going in and out.
Oh, now can you hear me?
Yeah, now it's good. You can hear you.
Okay. Because I am recording, so I have turned on the video. So therefore, everybody, you please turn off and mute. So it will be better. Okay. So do you understand this one?
Yes.
So which thing you could not hear? I mean, this slide or even the previous slide?
Just this slide. We could hear you on the previous slide. We just couldn't really hear you at all for this problem.
Oh, okay. So therefore, okay. So I'm repeating again. So you understand this diagram, right? Like VN and then VBN, VCN, Y connection, and then those quantities were given, VN, VBN, and VCN. And here you see the question was find out the line voltage, VAB, VBC, and VCN. So these are the phase quantity, phase to neutral voltage. So I am finding VAB. So everybody see this diagram? I'm sorry. So VAB means VN plus VNB. Because this is vector, I have to follow the vector. So VN plus VNB. But then here VBN is given. VN is fine. It is VN. I can substitute this value. But I have to change the NB into BN. So that's why I am putting the minus sign. Because this is vector, so you have to follow the particular direction. So that I am saying. And then if you substitute the VN value here, and then finally you will be getting this one, 480 at an angle of 30. So everybody understand this one?
Yes.
Okay, great. And then I was telling her that there is a mistake here. I wrote similarly VN, VCN. No, it should be VBC and it should be VCA. That I said.
Possible for you to zoom in a little? It's very small.
Oh, yeah. Okay. So actually, I will correct this one. I will be correcting this one because, I wrote by pen. So it should be VBC, like you see, BC, and then CA. Because the question is this one, like find out VAB, VBC, VCA. But then I just wrote similarly VB and VCN because VB, B and CN, those were already given. So it should be VBC and VCN. So okay, I will change this slide. I will change this slide.
But could you zoom in, or it's just hard to read the writing when it's so small. If you could maybe with the slider zoom while you're talking about a section.
Oh, okay. Just a moment. Is it better now? Is it better now? Can you see now? Can you see now?
Yes, now better. It's better.
Yes.
Yeah. Okay. Thank you. Then moving forward. So the one important thing I should tell. So you see here, so these are like VN, VBN, VCN. Look this one, 0 degree to 40 degree, because they are going anti-clockwise. It should be minus 120, but then anti-clockwise it is plus 240. And then this should be minus 240, but anti-clockwise 120. That's why all angles are positive. But here you see, when we calculated VAB, here the phase angle 30 degree. But then for BC, as I told, actually this is wrong. It should be VBC. See the phase angle minus 90. And then here it is 150. Therefore, how it is coming, you see, this is VAB 30 degree, but then VBC, it should be 120 degree apart, clockwise. This means 30 degree minus 120. That's why minus 90. And then from here, VCA, it should be another minus 120. So you see minus 120 and 90, minus 210, but then anti-clockwise, it is plus 150. So Everybody understand what I am telling?
Yes.
This means once you get this one, I mean, even without calculation, you can get this angle and this angle. Look, this is 30 degree. So therefore, next for VBC, you will be just subtracting like 30 minus 120. So therefore, that is minus 90. And then from here, you will subtract another 120, minus 120. So this means minus 210, but then anti-clockwise, it is plus 150. Yes. And then other important conclusion is that in case of the Y connection, what we learned that line to line voltage should be root 3 times of the phase voltage. Therefore, here the phase voltage are 277.13 volt. But then here you see the result, just look for VAB 480. So therefore, 480 is root 3 times of this one. If you have calculator, you just multiply this number 277.13 multiplied by root 3, you should get about 480. Do you understand? Could you follow me?
Yeah, I think we understand. You just cut out at the end there again for a couple
Uh,
seconds.
Okay, okay. So therefore, just multiply by root 3,
We
277.
still can't hear you.
Oh, okay. Yeah, sometimes like internet connection is a little unstable. Yeah. Anyway, like 277.13 multiplied by root 3, and that will give you 480 about. Are you getting that one?
Yeah, we get that.
Yes. So this is the thing that we learned, that for example, if you see this one, for Y connection system, line voltage VL is root 3 times of phase voltage. So therefore, this calculation proves that fact that, okay, these are the phase quantity, but line quantity is root 3 times. And here, like really by calculation, you prove that. But always you may not need to make this type of calculation. Just if you see this any number, multiply that number by root 3. Similarly for VBC and for CA, you see the 480. Just the angle will be different. And how to calculate the angle? First it is 30 degree. From there you just go clockwise by 120 degree, 120 degree. So that's all. Now for this problem, there was the second part. Now let me. Okay. You see what is the second part? If a balanced Y connected three-phase load of Gn equal to Gbn equal to Gcn equal to 10 at an angle of 30 degree ohm is connected to the source, then find all the phase and line currents. So this means this is the source, but part B problem says that there is a balanced Y connected load, and that load, each coil has impedance which is 10 at an angle of 30 degree. So therefore again here see, let me zoom in. Okay. So therefore everybody see, this is the left side that was given. I mean, this thing that we dealt with, and then those lines are going and they are connected to three-phase load. And again, it is Y connected and it has a neutral point. So it has neutral point. So you could connect both neutral, because ultimately both neutral will go to the same safety ground. That's why you can connect the neutral line. And then each coil, you see, each phase has impedance Gn, Gbn or Gcn 10 at an angle of 30 degree. So this means that everybody see, because left side is Y and right side is also Y, this means, and this is the neutral connected. So for example, look this one Vn and look A prime N. So this voltage and this voltage is the same. So that's why your question is find out this line current. How much current is entering into the load? Line current and phase current. So but everybody see, for example, the line current is going, it is coming from here and then going, and then entering into this page. But then once the current come here,
Dr. Ali, we couldn't hear you for a moment. In other Zoom calls, we've seen that if you turn off your video, there'll be more upload bandwidth for the audio. I think we might should try that.
oh, okay. So just a moment. Okay, is it better now?
We'll let you know after a few minutes. Go. So far, so good.
Okay, I just turned off my video. I turned off my video. Could you hear now better or?
It seems better, yes.
Okay, but if I turned off my video, okay, so my recording is going on. I think this will be fine. Yes, okay. Okay, could you follow me what I was telling here? I mean, the left side is the source. I mean, this thing, the upper figure that we discussed already. On the right side, the Y connected load. So, and then the question was here, see this one. The question was find all the phase and line currents for this case that we are trying to do. So therefore, what I am doing, ILA, IFA, this means line current and phase current are the same. Everybody, can you see? This is the current coming, IL, here it is called line current, and then the same current is entering into the phase coil of the load. So that's why I have written that ILA equal to IFA. This means line current, phase current are the same. And then what's the voltage across this one? A prime N. The voltage which was available here, Vn. That thing is given here. You see, Vn, Vvn, Vcn. So that's why Vn over Gn. Gn is the impedance. So this impedance is 10 at an angle of 30, and then Vn is this one. So just you divide, and then by Phasor algebra, this 30 will go in the numerator and it will be minus 30. Could you understand this one? Is everybody fine?
Yes.
Yeah, definitely. Mhm.
Okay, great. So similarly for phase B and for C, it is the same. Yeah. Okay, and then let me look another example. Okay, just a moment. Okay, everybody see, if you understand this problem, then after this class, I am going to assign you the first set of homework about three-phase system. Then you could do most of the problems if you understand this one as well. So everybody say, what is the statement? A balanced delta connected three-phase load withdraws 200 ampere per phase with a leading power factor of 0.85 from a 12.47 kV line. Then determine the following: line current of the load, phase voltage of the load, three-phase apparent power, three-phase real power, three-phase reactive power, and three-phase complex power. You see, like most of the quantities are being asked in this problem. So once again, read: a balanced three-phase delta connected load withdraws 200 ampere per phase. This means this is the phase current of the delta connected load, and power factor is given, which is 0.85, and 12.47 kV line. As I told you, this line means this is line to line voltage, but because this is delta connected system, so line voltage and phase voltage are the same. So now here is that solution. Let me zoom in for you. Everybody, could you see the diagram? This is that delta connected load. This is the delta connected load, You see that 200 ampere, this is the phase current. I mean, in any of the coil. And then these are the line, three-phase line. But then you see, I am indicating that line voltage VL 12.47 kV between two lines. So power factor value was 0.85, which is cosine theta, and I made it sine theta is 0.53. I mean, you will be finding theta and then sine theta. Now the first question was find out the line current of the load. So therefore, everybody see, this is the phase current, 200 ampere. This is across the coil. But you are asked here, the line. So now I want to apply those rules that we have learned, that in case of delta connection, line current is √3 times of the phase current. So that's why 200 multiplied by √3. Directly I am doing that. So that gave me 173.1 ampere. But, and then the power factor was given. It is the leading power factor. If you see the statement, leading power factor of 0.85. So that's why here you see cosine theta is 0.85. From there, find out theta, cos inverse 0.85. That will give you the angle 31.78 degree. That's why you see in bracket, I have written IL, this magnitude, angle 31.78. Now here, this is the plus angle because leading power factor. If the problem statement, if you see here, it is lagging with a lagging power factor, then at that time, please use the minus sign here, like minus 31. Could you follow me, everybody? Is it fine?
Yes.
Okay, thank you. The next question is find out the phase voltage. So what I wrote, the direct answer, phase voltage is 12.47 kV. This means the line to line quantity were given 12.47 kV, and then line voltage and phase voltage is the same for in case of the delta. We already discussed. That's why this is the direct answer. Now question number C is find out the three-phase real power. So what is the equation? You see, √3 VLIL cos theta, that we learned. So therefore √3 VL is that quantity, 12.47 kV. IL we calculated 173.21. What is the cos theta? Cos theta is that 0.85. 0.85. So if you multiply 3.18 megawatt, I converted into watt. So this is megawatt. And then come back. Three-phase reactive power, √3 VLIL sine theta. So therefore, this will give you √3 then VLIL, that sine theta value. So how I get sine theta value? At the beginning, I calculated from the cos theta. So that is my sine theta. So I got 1.98 megawatt. Now the last question is three-phase complex power. What was the three-phase complex power? So here you see what I have written, √3 VL IL conjugate. This is star science means conjugate. If you remember the circuit codes 2, I explained you that complex power is VI conjugate. VI conjugate. So in this case, this is three-phase complex power. So √3 VL IL conjugate. This means IL conjugate means, everybody see here inside bracket I have 4 IL 173.21 plus this one. What is its conjugate? Complex conjugate, IL conjugate. Just you will change the sign of the angle. So that's why see here I put 4 IL on 73.1 angle minus 31. If angle would be minus here, then you will be putting plus sign here. In this case, angle is plus here because I need conjugate, so I am changing the sign. And this is √3, this is VL value.
Hey, Dr. Ali.
Yes.
So for part A, how did you get 173.21 for that?
You see this one, root 3 times
Yeah.
200. Can you see that 200 was given for the line current?
Yeah, but the square root of 3 is greater than 1. So when you multiply that, you get 346 and some decimal.
Oh, so okay. So this amount, right? Yes. So what value you got?
So I multiplied 200 by square root of 3 and got 346.41.
Oh, okay. So probably I wrote this number wrong. Yes. Oh, so you are right. Just a moment. Was it 300? Sorry. Yeah, it was 200. Right, 200 per page. Right. Okay. Therefore, I put this number wrong then. Yes.
Yeah, you divided it by 2.
Ah, okay. Yeah. Probably then although I wrote 200, then maybe I did all with 100. Yes. Okay. So how much you said? 346?
Yeah, 346.41.
Oh, okay. So I divided by 2, right? Yes.
Yeah.
Yeah, probably then when I did, I used like 100 and then accordingly I went it. Okay. So therefore I will be changing this on then. Yeah. So everybody please take a note. I will be changing this slide also. I will make it bigger font and I will change this on. Yes. So I'm sorry for this mistake.
That's okay. What are the units for the answer to part D?
Megavar, mvar, megavar, megavolt ampere, reactive volt ampere. This is this is reactive power. So unit is var, var, but I'm converting into mega. So that's why megawatt. Is this fine?
Yes, sir.
Yeah. So the part C is megawatt, watt, and then I converted into mega. That's why megawatt. This is accordingly megawatt. I mean, the basic unit is watt, basic unit is var. Yeah. So therefore, then everything I think will be changed, right? Every number. Is this? Like if this is 346, then I think this will also be changed, this number.
Yeah.
Yeah, all of them are
everything will
going to change.
Yeah. So please change all current value. Yeah. Other values are the same, but just change the current values. Okay, so therefore let me redo it. I will be redoing this one and then I will be posting. Yes. Okay. Don't worry. You just make it correct. Take a note. Anyway, so therefore, then accordingly, like this number will be changed. Just keep in mind. Yeah. But I was explaining that IL conjugate. Do you understand this one? So you see here initially for part A, this is the magnitude, whatever 346 point something. But then you have to consider the angle to represent a vector quantity. And that angle 31.78 I got from here. You find out the theta from the cos theta 0.85. But then it is plus sign. I put plus sign because of the leading power factor. If the statement says lagging, then you would be putting the minus sign here. But because it is leading, so plus sign. But then after coming here, three-phase complex power, √3 VL, I will conjugate. I have to change the sign because it is complex conjugate from the math. So everybody, could you follow this one? Is this fine?
Yeah.
Yeah, it's good.
Yes.
Yeah. So therefore, because I will be assigning the homework, I might say the lagging. So that time you will be putting minus sign here. Then you will be changing to plus sign here. Today it is plus here. Therefore, I am doing minus here because of conjugate. And see this one and this. Look, the amount, this is MV. So the unit is volt ampere. Keep in mind, for the complex power and apparent power, the unit is volt ampere. So I am expressing in megavolt ampere. And then other important thing you notice, clearly this is the complex power because there is magnitude and then the angle. So from there, from this line, I mean, I just making on verification. That's why I have written this bracket things. This is the polar form. Convert this form into rectangular form. Then you would be getting 3 point on it and 1.98 reactive power with a minus sign. So now if you go back, the first part 3 point on it, which you got in part C, exactly same, the three-phase real power. Now the second part, we just got three-phase reactive power 1.98. This is the magnitude. So therefore, whether these calculations are correct or not, to verify that, you can convert this on in this format. Or in other words, you can leave the result in that format as well. That will also verify the fact that, okay, this calculation and this calculation was correct. Therefore, everybody, as you see that, because I wrote this number wrong, this number, I think I probably when I was doing calculator, then somehow I put 100. Therefore, accordingly, after that, I did not notice that, and so all calculation went accordingly. So please, you change 346 something you told, and accordingly you change all number. So just these values will be changed, but the process will be the same. The method is the same, process is the same, just these values will be changed. And in the class lecture, I will be changing this slide with the correct number. So everybody fine so far?
I have one just small question. I'm so sorry. It was for part D for the sign. Did you use the power factor to be able to find?
Oh, this sine theta?
Yes, sir.
Yes. So therefore, look this one. Initially, the power factor was given 0.85, which is cosine theta. Therefore, from here, first you find out the theta, what is the angle, and then make it sine theta. That will give you 0.53.
Oh, that makes sense. Thank you. Thank you.
Got it? That's why initially I did it here. Yeah. Can you someone check that I did it correctly? This thing is right. Right now, can you check?
Yes, it comes out to be 0.526. So yeah.
Okay. So I
0.53.
choose, yeah. But only thing like I put 200 here, but then I think I divided by 2 accordingly. So I'm sorry for this mistake, this number. You note down, and of course I will be changing. Yeah. But the method is the same. Yes. Is there any questions on this problem from anybody?
That looks good.
Okay, thank you. Therefore, once again, you look after the class because I will be uploading that video. Again, you can see, or you can see the preloaded my audio voice, those slides. So I mean, in both places you are getting, and right now you are looking kind of the 3 chances. One is beforehand I am uploading those class lecture material, and then this class during the Zoom class plus the after class you are looking the video. So there are a lot of opportunities for you. Anyway, so then moving forward, let me, yes. Okay. Everybody see, so here there is another problem. Just for practice, I set up, everybody read. A 3-phase motor can be regarded as a balanced Y load. A 3-phase motor draws 5.6 kilowatt when the line voltage is 220 volt and the line current is 18.2 ampere. Determine the power factor of the motor. Therefore, this is just pretty easy. Already we did the bit complex problem. So just I wanted to show you how to calculate the power factor. That's why I have set up this small problem. So everybody see, you have to find out the power factor. So that's why, and then the motor draws 5.6 kilowatt. This means this is the real power value because the unit is in kilowatt. So therefore, write down the equation real power phi √3 VLIL cosine of theta. And then just substitute those values, those numbers. Phi value is this one, 5.6 kilowatt. This is root 3. VL value is 220. IL value was 18.2. You have to find out the power factor mean cosine theta. So finally cosine theta is 0.8075. So everybody fine with this one?
Yeah, it seems okay.
Yeah, this is, I mean, the pretty easy, even much less complex than the previous problem. So just in this case, we are finding the power factor from the expression. Okay, I think there is the last problem for today. So everybody see, this is another problem. Look this diagram. What I am asking, calculate the line currents in the 3-wire YY system of figure 1. This means, you see, in this case, left side a 3-phase Y connected source on 10 volt at angle of 0 degree, minus 120, minus 240. So, and then they are powering a load. This is again Y connected load. This is balanced load. Impedance of each phase is 10 plus J8 ohm. And then between this point and the load point, there is a series impedance. For example, this one, 5 minus J2 ohm, 5 minus J2 ohm, 5 minus J2 ohm. So therefore, all these things are given. Question is, calculate the line currents. This means how much current is flowing. Just one question. How much? This is the line. This is the line. This is the line. So therefore, now see the solution for this one. Let me zoom in. Yes. Can you see? Just I have redrawn the diagram, and then can you see this? This is the neutral point. So look, this good figure. This is the neutral point on the left side. On the right side, this should be the neutral point. So therefore, these two neutral point, you can connect these two neutral point, this neutral and then this neutral. So therefore, accordingly, this point and then this point, and this is N and this is N prime. I have indicated. And see just one thing for one phase, VAN, this one line is going. This is A point. This is A point. This is the GI. And then this one. So where GI is, what is GI? GI is the combination of these two. Could you understand? So simply I have written GI. Therefore, you look, the GI is 5 minus J2. This means top one. And then for the load on 10 plus J8. Then if you sum up these two, then you are getting this one. So this means because you have this voltage available, and this is neutral point, this is neutral point. So this is that voltage, and then this is the total impedance. So how to get IA? IA is what voltage was available on 10 at an angle of 0 degree. Divide by what I get from that combined impedance, series impedance. So that is my current. Then similarly go for B and go for C. Exactly the same way. That voltage divided by the just the it is difference in terms of the phase angle. You see, minus 120, minus 240, because the voltage was here minus 120 and then minus 240. Accordingly, the magnitude is the same, just angles are the different. So everybody, do you understand this one?
Yeah, definitely. Looks good.
Yes, yes. Okay. So I think I don't have further slides, so that's all for today. Okay. So is there any questions, comments from anybody on any specific slide or any specific questions?
I was just going to say that the audio was not interrupted after you turned off your video.
Okay, okay. So therefore, the next time I will turn off my video. Yeah. Is this fine? Yeah.
Yes, sir. Yes, sir. And you also said the homework was going to be posted.
Sorry?
You said, oh, sorry. You said the homework was going to be posted later on today, or you said?
Yeah. Hopefully today. Hopefully, once I do, then I will be notifying you. And then after posting the homework, at least you will be getting like at least 1 week to submit. So you will be fully fine. So therefore, at home, everybody, please again, you understand each and every slide. And then once you understand, and you attempt to solve the homework problem. So is this fine?
Yes. Thank you, Dr. Ali.
Yeah. So therefore, everybody, please understand all of the slides from the beginning. See the relationship between voltage, current, delta system, Y system, and look the numerical problems once again. And then please try to solve the homework. And then hopefully by evening, I will be posting the homework, and then I am going to notify, I will send you an email. So then you will be understanding that I have uploaded the homework. Okay, so with that then now we like to conclude today.